Today I'm going to show how to consume a REST API in Python. Basically, I'm going to produce a pandas data frame from a JSON feed. So why Python? Python has great libraries for data analysis, pandas being one of them. Pandas also builds on NumPy, and matplotlib is another library often used for plotting and charting and analyzing data. Why use JSON instead of a CSV file? Well, a CSV file, you have to download it, and it's not the most recent data because someone's generated the CSV file earlier. Generally, JSON will have richer data because it supports hierarchical and relational data in a structure that can be nested many, many levels deep. You can support queries to get the more JSON that you want and format in a way that you want. It's less error prone. And finally, JSON will scale much, much better than a CSV file. So the goal of parsing the JSON is to come up with a pandas data frame. A pandas data frame is basically a two-dimensional array or a spreadsheet of sorts, which has a bunch of columns and rows. Rows being the index here, 0, 1, 2, 3, and the columns can contain all types of values. Now here we have a Boolean value, which is yes or no, numeric values, categorical values, and ordinal values. Categorical value is something like type of food, and ordinal value would be the spiciness now, or the strength, for example. I'll explain that in a little bit greater detail. Let's say you wanted to have the sum total of all numeric values. Well, you could just add them up and come up with 12,123 plus 432 plus 2. However, we're going to run into a problem with this data because these quotes mean that they're strings. So JSON sometimes, especially in the case that I'll be showing today, returns string values. What we really need is to have integers. Integers you can add. So if I wanted to have the sum of the numeric values on this data, I would get an error. Similarly, as a human, I know that very mild is not as strong as medium, but if I wanted to compare this, and right now we have 4 columns, but in real data we'd have a lot more. If I wanted to compare this against a very large data set, I need this to be numbers. So I would like something other than an error if I was trying to compare very mild to medium. So what I want to do is transform this into something that I can now run mathematical data analysis tools on. So this transformation will look more like this. We would have, the numbers would be integers, the booleans would be booleans, and this is pretty straightforward. For categorical values, we would just assign numbers. Fruit is 1, vegetables is 2, dairy is 3. For ordinal values, the numbers actually correspond to the intensity of the scale. So for example, if medium is stronger than mild, it has a number that's larger, and if strong is stronger than both medium and mild, it will have an even larger number. So the numbers, if you were to plot them on a graph, would actually correspond to the values without having a legend. With categorical values, one without knowing that it's fruit is meaningless. You need that mapping. Mapping is something that will come up a fair amount later in this demo. So what we're going to do is we're going to take our data coming from the JSON, which is strings, and transform it into numbers. Now, obviously, it's very easy to just go through and say, okay, we know this column number 2 is integer, so we're going to just turn it into integers. And we know that we have fruits, vegetables, and dairy, so I'll just say every time I see fruit, save 1. Every time I see vegetable, save 2. And every time I see dairy, save 3. And that would work, right? Except for, we're talking about large data sets here. So what happens if this script is running and then tomorrow somebody on the other side says, yeah, well, I have this sirloin here and it's not really a vegetable or fruit, maybe it's a meat. So if you've not anticipating that new value to be in the JSON and it suddenly appears, you're going to get an error. So what the correct thing to do would be, instead of having a static map, is to dynamically, on the fly, look and say, okay, fruit, okay, I'll give it 1. Vegetable, I'll give it 2. Dairy, I'll give it 3. And then when something new comes in, just assign another one. Okay, meat, 4, done. So in essence, you don't really know what the values will be until you actually parse the JSON. That way your code's going to be a lot more resilient against unexpected values. Of course, the other dimension is also true. You could actually have a row that has extra columns in it. You kind of need to handle that too. So what you'd want to do is you'd want to dynamically create a new column for that value. So that's the overview. Now let's look at the code. In this case, I don't know Python, so I learned Python basically this week working on this project. And coming from a Java background, of course, my code's very object-oriented, so there might be a bit of a learning curve on that, but I'm going to walk you through it. So first of all, objects. Everything that's an object in object-oriented programming generally inherits from one super object, and Python has that object. That object has some properties and some methods. One property is the documentation about that object, and some methods that all objects know is how to create an instance of that object via init in Python, and how to write itself out to a string, which would be the str method in Python. So the first object that I've written is a column type. Column type inherits from object. It also knows how to write itself out to a string. It knows how to transform a value, and you can also override it in the case of we want to have ordinal values. We want to have medium or hot or very hot or strong, very strong. It also has a name, and it has a list of possible values. Well, we need to keep these values around. For instance, if I have a column type of food type and I've already returned vegetable as 2, I need to continue to return 2 for vegetable every time I see it. So that possible value map needs to be stored in memory as we're parsing. So column type looks something like this. Not much there, but it has a init function, which is overridden from the object class. And it has a name and a data type and a dictionary of possible values. So that would be the dictionary as it was parsing, which is populated with 1 fruit, 2 vegetables. And it has some code just to print itself out nicely, and we'll see that later. So how do we keep the columns into a nice table? I mean, we've got 60 column types. How do we know how they sit inside of a table? And how do we map the values coming in from the JSON to the correct column type? So I've created a column mapper. And a column mapper basically just has a bunch of columns and some similar methods. It does have the ability to populate itself from the header JSON. Sometimes JSON files have some information about what columns to expect coming forward, and that may have a lot of detail or less detail or not even exist at all. So now that we have a column type and we have a column mapper, now where do we get the JSON from? Well, JSON comes in feeds, and a feed is basically just a URL that you build up dynamically, and then you call it and it will return JSON. So now we're up to 3 objects: column type, column mapper, and and feed. So a feed has a query, and it also has rows. Rows are what represent each row that is in our data frame that's coming from the JSON. It also has an init method with a base query, and you also give it a column mapper so that you have a column mapper that it knows how to map the JSON. It has a run method, which will then go get the JSON from the base query and populate the column mapper, and then it has a method that after you run it, you can get a data frame. There's also a tricky method in here. It's abstract. It's called parse. So the JSON that's going to come back is going to look different for every different feed. So how do we get that JSON into a column type? How do we know what level the actual data is at? It could really be called anything. So I have this abstract method. That means it's not implemented. It means you need to make a subclass of feed for your feed, and you need to implement that method so that it knows how to read the particular JSON that you're going to be dealing with. So feed, a lot of very simple objects. A lot of very simple methods here. Nothing too complicated. A lot of these are meant to be overridden by subclasses, but you'll notice there's a parse method, and it raises a not implemented error. That means you cannot call it. This won't run unless you have a subclass of feed, but you have a run method, and all run does is call parse on all of its rows. It also at the bottom has a static method for getResponse. This is just a little trick to deal with the case that we need to make SSL calls to the feed, and Python is complicated to make an SSL call without installing certs, so this is a kind of workaround for that, so we can run this in Jupyter. So calling a feed once is fine, but generally feeds don't return the massive amount of data that we need. The internet would break if we returned all the data in a database after one call. Generally they'll serve up 1,000, 2,000, so many rows, and then you have to call the next page to get the next set of rows until you're out of rows. There are a few different patterns to do paging. One pattern is to have at the bottom of your JSON, and this is why you need to have a custom JSON parser for every type of feed. One way is to have a next page token. Another way of doing it is just saying I want 1,000 rows, and I want to begin at this number and end at that number. So you would run I would want to have 1,000 rows starting from 0 and ending at 1,000. And then after you run and parse that, then you would call your next page. I would also want 1,000 rows, but this time starting at 1,000 and ending at 2,000. And then you would like to have 1,000 rows starting at 2,000, ending at 3,000, etc., 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 until your query returns less than 1,000 rows. At this point, you know that you have reached the end of the feed. So page feed is an object that is a subtype of feed, or a subclass of feed, and here we have two objects. We have a page feed and a page feed configurator. Page feed configurator just says, okay, so I know I have to tell you what the page size is, and I know I have to tell you what the offset is, what page I'm on. So what are those names? And then it has a convenience method to just get me the parameters, so I can build up this URL as I repeatedly call the endpoint to get the JSON. This is a page feed configuration object. There's not much there other than passing in the names of the parameters and getting that URL string back to append to the query. Page feed is actually really interesting now. So it is basically, most of the methods are just the same methods that exist in a regular feed, except for the run method. In the previous simple one-page feed, the run method would just call parse once. But in this case, what I'm doing is I am building up the URL from the page configuration, and then I'm calling parse for all of the rows. And if the number of rows is equal to the page size, I've filled up that page, there's probably going to be another row. So run then calls itself again. It's a recursive method. Run calls run up until the point where at the current iteration there are less rows than I was expecting, at which point I think I'm at the end of the data. All right, so that's pretty much all we need to parse a feed. Let's put this into practice. So the feed I'm going to parse today is the killed or seriously injured morbid police data, which is basically a list of the Toronto police, all of their accidents that have seriously injured people. It has a fair amount of data on where and why these accidents happened and what level of injuries happened. So I'm now going to have a KSI column type, a KSI column mapper, and a KSI feed. But although this looks like a lot more complexity, there's very few methods I need to do here, because most of what the functionality that I need is already in the base classes. I already have column types, I already have column mappers, I already have feeds. So what I'm going to do is override that parse method, which I talked earlier, which knows how to read the specific URL from the KSI endpoint. I have to override transform value because, of course, my column types are going to be different, so I've overridden that. And I also have a convenience method to, they do have a header, and they do say a little bit about what columns are coming, so I'm going to load that to my column mapper. A little bit of code on that. It looks a little bit larger here, but this is actually the meat of the project in a sense. This is my column type. So what I'm doing here is I'm looking at the values as they come in, and I just check. Some of them are actually integers in the database. The JSON says this is an integer, so I know it's safe to cast it to an integer. Dates also, I know what they are. But unfortunately, most of this data is string. So I'm going to look and I'm going to say, is it yes, then it's a Boolean. Is it no, then it's also a Boolean. Is it a digit? Like, does Python say that there's nothing in here except for 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 0? There are no other characters. If those are the only characters in here, it's an integer. Again, if it's the same as that, but it also has maybe a period, then it's going to be a float value. Aha. But what if it's not? What if it is fruit? What if it is vegetable? At this point, it's a categorical value. So I'm just going to see if I've already come across this value before, and if I have, I already know what number it is. I know fruit is 1, I've seen it before, so I'll return 1. If it's going to be vegetables, and I've already seen vegetables, then I'll return 2. If it's something I haven't seen before, I'll say, okay, well, I've got meat now, I haven't seen this before, so I can't return 0 or 1 or 2 because I've already returned them, so the next one in the row is 3, so now meat's going to be 3. And that's how, as we parse through all of the columns, we build up this column mapper. Column mapper doesn't have too much in here, but it does pre-populate itself with that header from the JSON. And then the feed itself, just some specifics about querying this particular feed. It builds up the base query, and it has the ability to look for certain dates or certain indexes, and deals with their specific JSON. For example, the names of their rows is counterintuitively called features. So each row is called a feature. You wouldn't know that, you wouldn't expect that. So that's why you have to subclass feed with a specific class so that you can handle the way that JSON is formed. So that's a lot of just code, probably very boring. So let's just go on and finish this off with a quick demo. So all of this code's here, there's a fair amount of it, but at the beginning here, since all these objects are defined, we don't really need to worry about it. We have a main function. Main's gonna just get called automatically when we run this. So let's make a new object. Let's call it KSI, and it's gonna be a new KSI feed. And when we init it, we're gonna just say, give me everything from 2010 to 2019, and it will get all of the pages and make all of the calls. So we'll run it, and nothing happens. But it did actually parse that data, we just didn't see it. In fact, it did call a query, so let's just say print KSI get query. Let's just see what query it called, for the first page at least. And there's a query, so let's take a look at that. What does that look like? I'll put it into a browser, and we will see JSON. So there's our headers. It tells you what the columns are going to come, and then there's the actual data, and it's going to give us 2,000 rows. That's our first page. So what else can we do that's interesting with this? Well, we can, instead of getting that data, we can just, let's call. Python likes to have everything on perfectly indented. It might make me insane at some point. So let's just call run and parse that data, and then let's print out the data, but we're going to get the data as a pandas data frame. So there's a method here, which is get data frame, and we'll print that out and see what that looks like. So in 3 lines of code, what will happen? All right, that took about 2 or 3 seconds, and we got 10,000 rows, which means it probably got about 6 pages of data. And the data is nicely lined up. We can also look at the data types and see if it actually did the parsing correctly. I'm going to just cut and paste here. This is not amazing. Get types. Let's do that. All right, so we have objects, floats and ints for latitude. It has actually gone through and parsed that data correctly. Now, the final thing is, so it did all this mapping. How do we look and see what the mapping actually did? So what we're going to do here is we're going to print, after running it, KSI, and we're going to get the column mapper and column mapper has all of the values and the mapping it's done. But do you remember earlier that we had the string method, so it knows how to print out a string of itself? Because we're calling print, it's going to automatically call that string method, because Python knows that column mapper is a type of object, and all objects know how to print themselves out as strings. So this should work. Let's just pray to the demo gods it works. Haha, yes it does. So here's what's happening is it's gone through and it said, for every neighborhood I've assigned a number. For, the first time it comes across base recorder, it says, okay, that's 3, and then it's going to return that for every time. And so we can actually chart this and graph it. And then finally, what happens if we just don't want arbitrary numbers? What if we wanted to have a ordinal mapping? We could also do that by preceding the tabs again. The tabs. We could precede this with an actual mapping. So here we have a fatality if it's a minimal, minor, major, or fatal. And we're saying that a fatal is a 5, a major is a 4, and a none is a 1. So now we have an actual ordinal value. We'll precede that, and we'll run this. And it is, oh, and that's faster that time. So now I'm going to look for injury. Injury is an object. And in this case, we didn't, that's not the injury we want. Here we are. So it's been overridden, and these are in the correct order. 5 is fatal, and none is 1, as expected. What happens if we get that case where they invent a new injury that's like, I don't know, super fatal? Well, if it's not in here, the code's smart enough to say, I haven't found this, I'm going to assign an arbitrary value to it. That way we don't lose the data, and then when we call our column type later, we'll see that, you know, we fed it 5 values, there's now 6. We need to update our code, but it won't bomb. It will actually do the right thing. So that's the end of my demo, and thank you very much for watching.